Van een timer aan dat ik ongeveer weet hoe lang ik bezig ben.
Ja.
Dat is belangrijk.
En laat ik even heel even zeggen, als we nu kunnen beginnen. Dus welkom iedereen. Vandaag doen we de master thesis verdediging van Nardi Lam. De presentatie gaat in het Engels plaatsvinden.
Ja, doe maar het Engels hoor. Dus,
ik spreek nu nog even in het Nederlands.
You have to speak English, please.
English, let's do it in English. So I would like to ask everybody who is not speaking to mute their microphone. And first we'll have a presentation of about 30 minutes about the content of the thesis. And then there will be 15 minutes for question and answers. And after 45 minutes, me and Chris, who are the readers or the supervisors, will discuss the evaluation, and then there will be a final part of the meeting. So without further ado, let's first listen to the presentation of Nardi Lam.
Nardi Lam.
Lam.
It also has to be in English, of course. Okay, yeah, so welcome everyone. I pretend this is a person, and then you are sitting here as well. So yes, welcome to my presentation. I'm going to talk about my thesis today, which is named Black Box Systems, Multi-Level Explanation and Cognitive Architectures. A bit of a mouthful. So to start, let's look at a few of these concepts, what they're about, and let me just introduce the topic to you. When you, in AI, especially in machine learning, you see a lot of systems being used that you can call black box systems. And what this basically means is that you systems to perform a certain task and to basically, given some kind of input, produce some kind of output. But other than that, the way in which these systems are constructed is not really, doesn't really happen on any kind of way which is based in the problem itself. So it's usually, they can do a lot of interesting things, but they can be a bit difficult to deal with because they are hard to understand what they're actually doing. So you could say that their internal structure is not meaningful in any sort of obvious way. So in some sense you should think about like a box which you're looking into, but you can't see anything because so you don't know what's going on. I think that's the metaphor. And this causes some problems for, I guess in a general sense you could say trust, right? If you have a system in your house or whatever doing things, but you don't really know how it works, it's hard to trust it. And you have these systems that are, really getting sort of integrated into like maybe your living room or whatever. So you want to kind of know what they're doing. But also in a very strict sense, sometimes you want to verify decisions that these systems make. So for example, if you have a system which is meant to make some kind of decisions on, for example, if you're a bank and you want to decide who gets a loan and who doesn't, you maybe don't want a system that is somehow sexist or racist or whatever. So you want to be able to verify these decisions, because this becomes difficult when you can't really look inside the system. So this is where a field called explainable AI kind of emerges. And the idea of that is, you want to do these things that AI is trying to do, but you want to do them in a way that really makes these systems explainable in the sense that you can actually verify these decisions and you can sort of understand what's going on. And yeah, then I make some sort of references or connections to also psychology, cognitive psychology in my thesis. And the main motivation of that is, it's something that happens quite often in AI as well, but the motivation behind it is just that they kind of deal with these similar kind of models that are basically equivalent to the kind of black box models that you see used in machine learning nowadays. So let's start with just a little bit of an overview. So in my thesis, I make some arguments, and this is kind of the core of the arguments I make, I think. So I want to go over these a bit quickly. So first we have this idea of explanations and different types of explanations. So I'm going to talk about a few sort of different ways to think about explanations and why there's not really one right way to say this is the explanation of a system or an event or something like that. Then I'm going to talk a bit about explainable AI specifically, And also we'll see that these different kinds of explanations are relevant in that context as well. So for a black box AI, you can just have one explanation and then you're done, if you really want to understand it well. And from this also we'll see that the methods which exist now are a bit limited. And I'd like to argue that you need to combine them in some sort of way, so to integrate them to get a really full picture of the system. And then finally, I'm going to look at cognitive architectures, which is something from psychology more, but they tackle a similar kind of problem, I would say. So they also try to take these various sort of small theories from psychology and try to put them in like a big framework where they all can work together well. And I think that looking at this kind of research, you can get some good ideas as well on how to maybe do similar things with these in explaining these black box systems. Yes, so to start, what are explanations? That's a good question maybe to begin with. Let's think of an example. So for example, I have a cat in my house right now, and he's very cute, but he can also be a bit of a black box sometimes. So he does stuff, but you don't really know why he's doing what he's doing. So maybe sometimes I'm looking at him and I'm trying to figure out, why is he doing what he's doing? So let's say he's moving, he's walking around the house, he's sniffing everything. I then wonder, okay, why is he doing this? Well, I could come up with a reason. Maybe, maybe he's hungry, right? Maybe he's hungry, and maybe he's looking for food. So I could then see what he's doing, right? I observe his behavior and kind of work backwards from there. So, okay, I guess at some point he was hungry and then he started walking around looking for food. And then at some point before that, he was not hungry, but some time went by and he became hungry. That's a reasonable explanation, I think. So this is something you could call a horizontal explanation, which is basically just I take these different sort of states of the cat and I kind of link them together with these transitions where he goes from one state to another. And that's reflected here in a very general way, where you just have these S's are states and these T's are transitions. And then this whole sort of trajectory is some sort of behavior, which you can sort of explain in this way. But even if we explain it in this way, we can still continue to ask questions about the cat's behavior, right? So we can maybe ask something about one of these states. So we can ask, oh, what does it mean for the cat to be hungry? Something like that. Or we can ask something about one of these transitions. So, okay, if he's hungry, why does he go looking for food? So maybe you can just accept that, but maybe, it's not enough. And then there are different ways to answer these sort of secondary questions. So you could, for example, say something about the inside of the cat, right? So you could say, oh, well, he's hungry. It means his stomach is empty and something like that. Or you could kind of look at the cat on a more sort of general level, like, okay, the cat goes to look for food because, through evolution and all those things, he just is programmed in some sense to go look for food because otherwise he will starve. So that's just something that developed in that way. And this idea where you basically take another kind of explanation, which is somehow different to the first one, and related to the explanation we had before, is what you can call vertical explanation. So the vertical horizontal is sort of metaphor that if I put it in a picture in a little bit, you'll see what's meant by that. But for now, let's look at these, what I mean by a different level of explanation. There are a lot of ways to think about this. So, right, like just now, you could think of maybe something very small, like inside the cat, or something very big. And in my thesis, I mostly stuck to the conception by David Marr, which you see quite a lot in I think, especially in cognitive psychology, where he talks about a complex information processing system. And he says, okay, you can look at this at 3 different levels. And I don't want to go into too much detail, but I just name them because they come by later on. So you have this sort of this highest level, which is the computational theory level, or computational level a lot of the time, which basically talks about, okay, what is the system doing and why is it doing this, or why is this appropriate? And then you have 2 other levels that are those are these two, and they are more concerned with how a system is doing something. And so you could think about like the second level as being the explanation we just gave. And then maybe if you go into the cat's body, right, you're really looking at the implementation. And then if you go up into this kind of evolutionary standpoint where it's like, oh, why is the cat even doing this? It's more like a sort of about the computational theory of the cat, I guess. Okay, so yeah, so if you put this in a picture, you could think of it as these horizontal explanations existing on these different levels in a vertical sense. And then they're horizontal, and then when you connect them, you move vertically. So I hope that's a bit clear. Okay, so next, yes, let's talk a bit about AI specifically, because, well, that's what we're talking about. So when we talk about explaining AI systems, I think a good first step is to try and figure out, okay, what are we actually looking for, right? So what do we want to know about these systems, or how do we want them to be explained? And my main source for an answer to this question is this review by Miller. It's quite recent, and he basically took a whole lot of articles from social sciences mostly, and tried to answer the same question. So like, so what can we, like, what are we looking for when you're talking about explaining AI systems? So what do people like having them explained, or how do they like it to be explained? And he has has a few key points, and I want to pick out two right now. So first of all, he noticed people tend to prefer kind of more general explanations to very detailed ones. So it's often good to kind of try to give a general overview of a system before really delving down into the details, and only really doing so if necessary. And he also emphasizes this point that explanation is a form of social interaction. So it might be nice to think about explanation as you have a system, or you have the cat, and you write down basically this is how it works, and then you put it on the wall, and then everyone knows. But yeah, this is a little bit more complicated, because generally if you really want to make someone understand something, you really need to sort of have a conversation with them, and I explain something to you maybe, but then you respond to me as well, and together we kind of try to get sort of the right explanation for you, I guess, because you are the one having it explained right now. Yeah, so what I get from this is that, okay, what we would like to do with these systems is try to start at a high level of explanation, then move into the details when we need to, or when the person wanting the explanation requests it, basically. And to do so, of course, we need to be able to move from this kind of high level to these lower levels. So to have this kind of vertical explanation and not only horizontal explanations. Okay, so next let's look at an example. So this is also from the article by Miller, where he talks about, he kind of presents this, I think, as sort of an ideal example of a system being explained well. So he talks about this system, these different inputs, which are images, and there are some animals on here, and then the output of the system is just, oh, this is a spider, oh, this is a bee. So that's easy to imagine, I guess, what it does, and when it's doing it right, because you look at the image, you can see, oh, okay, this is a bee, it's doing it right. And the way he presents this system is using a kind of what I've called a feature possession model. So this is not really a term that you see more often, but I think it's a concept that's used a lot. So people often talk about something, certain features, right? So you could talk about this spider having legs, and here the spider has 8 legs. And then you could say, okay, because this image contains, a creature with 8 legs, it is most likely a spider. And this is what is done here as well. So what he presents is this. It's 2 parts. So first we have this table up here, and this is the feature possession model I was just kind of talking about. So you have these different types of animals, and you have some features, and the spider has 8 legs and the bee has 6 legs, and using these features you can then distinguish them. And then the second part of the example is this conversation between some person who is interested in the system and some agent who is trying to explain it. And you can see here that the agent gives these reasons that make use of this feature possession model, right? So, for example, if when the person asks, oh, why is this a spider? Well, because it has 8 legs. Okay, so that seems convincing, and it seems, if you look at this entire example, it seems like a nice way to explain things, right? So it seems, yeah, it seems good. Okay, fine. But there's a little bit of a problem, and that's that we are, he is basically assuming we have something which usually we don't have. So let's say we're actually going to do this, and we're going to train some sort of neural network, for example, to perform this task. What we usually do is you start with some data set, so just a lot of pairs of these images and what the animal in the image is. And then you, so you start with this data set and you just have it from somewhere. Just assume that you have it, or you put it together yourself. And then you basically choose some sort of computational machine, right? So some sort of neural network. And you say like, okay, how many layers, how many neurons, and how do they connect? And then this is usually kind of chosen arbitrarily, in the sense that's not really connected to the problem, but it's mostly a matter of what works. And then if you have some sort of learning algorithm, you can use these two together to form the connections between the neurons in such a way that the system performs the task that it's supposed to perform well. And what you end up with is a system that does what you want it to do, basically. But if you have such a system, you have something which works or seems to work, but you're missing this feature possession model that Miller, for example, assumes that you can use to explain it, right? So if you would have this, it would probably be somewhere around here. So more bit in the sort of upper part of the level spectrum. But this is kind of an empty area right now. There's nothing really there. So he presents this feature possession model, but to get such a feature possession model, you need to know some things. So you need to know something about the system's internal representations. So this could be like, a spider has legs, right? So you could, the concept of a leg is somewhere contained in the system. And then you need to know something about the kind of rules, or I guess you could say algorithms, that the system uses to then decide on its output. So, okay, a spider has 8 legs. But this is something we don't have in the sort of normal case when we use this kind of system. So I would say that explainable AI, for a large part, is building this kind of description. Okay, so let's look at a few examples. What they do in explainable AI actually right now. So one example is the category of what I call approximating models. So the idea is basically that you take the black box system, you build a model which kind of tries to produce this similar behavior, and then you use that kind of simpler model to explain what the other system is doing. So the example here is something called saliency map. So there are horses in this picture here. And the system tries to, it tries to find the horses or something like that. And it looks here and here and here, and it sees, oh, here are horses. So, okay, that explains something maybe, right? If it was looking at the sky, it was probably not doing a very good job, or at least not in the right way. But it doesn't explain that much. So these systems are descriptive in the sense that they describe the behavior of the system. And maybe they do so quite well, but in the end, they can't really say much about the actual processing that the system is performing. So it can't really say like, okay, what is it doing when it looks at these pixels right here and it decides this is a horse? That's not really a question you can answer using such a model. So that's one category. Another example is this example of rationalization, which I think is interesting. So the idea is that as humans, we do it as well. We do something, and then someone asks, "Oh, why did you do that?" And then you basically think of a reason, but you can't really say that that was sort of the reason that was in your head at the moment you performed the action, right? So it's kind of after the fact explanation. But a lot of the time it's still like we accept it, right? So if you say, oh, I did it because this and that, then probably you did. Maybe like you can't really know that you knew it at the point when you performed the action, but we're okay with it. And what they did here was they trained the system to play this game, right? So it's like Frogger, I think. So the frog can move in certain directions and tries to avoid those obstacles. And then next to having the system learn what moves to play, it also learned to associate these kind of reasons with the actions that it took. And this seems sort of convincing, but it's also a little bit limited because, well, what you have here really is an explanation that looks nice, but also doesn't really say anything about the system that has to choose these moves. So because you could, just have one system choosing the moves, one system producing these kind of explanations, and really not have them connect, and they would still look convincing, maybe. So needs to be some stronger connection to actually link these explanations to the system which is performing the processing. And then finally, this is kind of, I think, most interesting kind of example, a method which they call feature visualization, where they look at these specific, oh, there goes my thing, these neurons in the network, and they try to figure out, right, so this is one neuron, each of them, what kind of images does this neuron respond really well to. So here you can see some parts of a car, and then together they kind of form this kind of car neuron through the connections in the network. So this is, I think, the most sort of connected, at least, to the actual processing, because you're really looking at these kind of neurons that are in the black box system and how are they connected and what are they doing. But yeah, so this is kind of a sort of an overview of what it's doing. But the way in which these things are limited is that they basically take a lot of work to really figure out where are the interesting parts. So, right, a lot of the time, if you look at the neuron and maybe, oh, you get a nice view of a car wheel. But a lot of the time when you look at some neuron, you get just a big mess of things and you can't really say anything about it. So, yeah, so we saw that all these methods are limited in some sense. Either they kind of lack this connection or they just take a lot of time to actually produce results. So also for this last one, they actually say in the paper, what if you could spend thousands of hours looking at a single neuron, which, I mean, is a nice idea, but you can't always do that, of course. So this is then the reason why I would say, okay, these methods on their own are not going to make it. You need to sort of connect them in some way, right? So you need a little bit of the different kind of approaches, either to, not have to spend a lot of time or to actually get some sort of connection to what the system is actually doing. Okay. Yeah, so the only part that's left now is to talk about cognitive architectures. So cognitive architectures are these kind of, let's first talk about what they are. So the kind of shortest way to say what they are, I think, would be computational formalisms for expressing models of cognitive phenomena, which is still maybe not that clear, it's quite condensed, but you could think of them as if you have this kind of cognitive system, which is showing some behavior, and you look at it as kind of a computer running some sort of program, then the cognitive architecture is basically the computer who then runs this program that is kind of tuned to a specific individual or a specific agent, basically. So just to give a bit of an idea, here's sort of I think he calls the prototypical architecture, which basically just shows some examples of the kind of parts that you can usually find in there. So for example, you have some parts relating to perception, which is where information comes in. Then you have some kind of memories that store and process information. And then in the end, some action is selected. And then this is performed, and then sort of the whole cycle happens over again. Okay, so now the next thing to talk about is what do these cognitive architectures actually explain? Because we're talking about explanation here, right? Not just building a system that does something, but also explaining something. So I guess the main thing in which these are useful is that they provide these kind of building blocks for how you can then build all these kind of different systems that produce this very varied behavior, but they still give sort of a limited set of blocks that you can use to put them together, basically. So you could talk about this as a certain kind of paradigm, so a kind of information processing style that the architecture posits. Or you could talk about this as kind of a language, right? So this architecture, it provides kind of words in some sense, which you can then string together to build descriptions of entire systems. So you can use it, for example, for sharing knowledge about these cognitive processes. So yeah, so now I want to look at two examples from cognitive architectures that I think are interesting and maybe useful in this context of explaining black box systems. So the first example is from Clarion, which is an architecture that has this kind of hybrid structure where they call it everything has an explicit and an implicit part. So here's an example where you have this part above the line is explicit in the sense that it's more similar to this kind of feature-based model where you have these kind of propositions about the system, like, oh, a spider has 8 legs, and then you use these and some rules to conclude something about the input, or yes. And then you also have this bottom part, which is basically the kind of black box system we have been talking about. So it's less accessible, but it is more flexible in the kind of processing it can perform. So this kind of dual kind of idea is something which you also see in explainable AI, because you generally have these two kind of systems, right? So the black box and sort of the system which does the explaining, who function in these different kind of ways. And yeah, but what I think is interesting in this case is that what happens is that both of these systems kind of convert their output to a sort of comparable form, and then they're combined into a kind of integrated output. So both of the systems, both of the parts of the entire system, you could say, contribute to the eventual output. And I think this is interesting because it's something you don't really see in explainable AI. Usually the explaining system is completely detached from the sort of the system it's trying to explain. But if you kind of put them together in this way, you could say, okay, because both systems contribute to the output, right? So both of these contribute to the output, it becomes a bit more explainable. So this top system produces an explainable output, you could say, and this produces a not so explainable output, the bottom system. And then together, it lends some more credibility to saying, okay, the output is this because the top system says so, because it actually has a hand in the outputs which are produced. So that's an interesting idea, I think. And then secondly, I want to look at this example from ACT-R, this is kind of sort of a global structure of how the architecture is formed. And it basically, instead of this kind of input-output loop, which you see a lot, it contains all these different resources that are very different in nature. So you could have, for example, something with vision or speech. So this is input and output, or you could have something that's entirely internal. And these all then communicate through this kind of central coordinating resource. And I think this is interesting because you could maybe do a similar kind of thing to have these different explanatory systems, sort of, in explainable AI, communicate with each other and produce a sort of more cohesive general explanation of a system. So, right, this is just very like speculative idea, but the kind of systems that we looked at up until now are these kind of approximating models and this feature visualizer. And if you could have them communicating in some way, and also with this kind of sort of module which then tries to actually establish an explanation and communicate it to the user, you could maybe build more cohesive explanations, basically. I have some more ideas, but I don't have time, so. Okay, so now to conclude, I just want to go over my arguments again for a little bit, right? So we looked at these different kinds of explanations. I try to argue, okay, they are different in nature. You need to have multiple levels of explanation and connect them to really understand the system well. And also in explainable AI, we saw that there's, if you look at the level diagram, there's basically this middle part which is a little bit missing most of the time. So if you want to move up and down, you can't really do that if there's a middle part missing. I think that's the easiest way to think about it. So that's the reason to do explainable AI in the first place, but then you still need to keep that sort of goal in mind of having this kind of vertical connection between explanations. And the methods we have now don't really do that, so you need to connect them in some way. And then finally, I had some things to say about cognitive architectures and some examples of how I think ideas from there can maybe inform this explainable AI venture that people are taking on now. So in the end, that's my message for the people who are actually working on that. So maybe not most of you, but I think that's the kind of purpose of my thesis in some sense. So yes, so thank you. That is my presentation. And if you have questions, I hope so, then I will be very glad to answer them.
Yes, thank you very much. Let's unmute ourselves and first applaud.
Oh yes.
And so now we have some time for questions about Nardi's presentation. So if there's a question in the Teams meeting, please.
I definitely have questions, but I also saw that there's students on the call and maybe family members, so I'd like to allow them to take the floor first.
Yes.
If any of them has any questions.
I have a question.
Liana?
Yes, hi.
Okay.
Can you go back to that Clarion slide?
Yeah, this one?
Yeah. Yeah, so I was wondering, do you know something about how these rules in the explicit part, how you create these?
Oh, yeah. So, so at least, I mean, there's quite a lot of literature on this architecture, and it's a little bit hard to actually find some very concrete sort of things sometimes. But the thing that I read, which I cited above here, basically talks about, well, the rules are learned in a similar sense as the maybe like the connections in a neural network will be. But the difference is that you have these kind of inputs and outputs that are in some sense already meaningful. So they only talk about like one layer and not like sort of intermediate things, but they just have, these are like binary factors, you could say, which represent sort of propositions about the input, which are true or false. And then, using some combination of these, so kind of like logical just combination, you can then get some propositions, some new propositions basically about the input. So I think the rules are not really like that, or the rule sort of finding mechanism is not that special really, maybe. Maybe what's more special is that they actually kind of posit, or at least need you to also figure out some kind of transformation from what they call the implicit representation, so in terms of like neural activations, to this kind of binary representation of the input and for the output as well. But yeah, it's more about how they sort of connect the different parts than really what they're doing. There's no like magic in there that all of a sudden you know all these features and the rules associated which you didn't know before. So it's more kind of a hypothesis about how maybe if you connect them in this way and just let it learn, the results that you get are somehow more reliable than maybe the results you have if it only goes one way, or if the connection is not strictly there, if that makes a little bit of sense.
Okay. Yeah, thanks.
Okay.
I have a question.
Well, go ahead.
So I was wondering, because you are combining these two in this slide as well, what do you think about sort of the accuracy of that model? Would it perform better? And if it performs worse, there seems to be some sort of trade-off between, you get some explainability, but you lose some accuracy. What do you think about this trade-off if it is there?
Okay, so you mean in general, like when you do explainable AI, the trade-off between this more like explainability of a system and this accuracy of system, right?
Yeah, maybe you lose accuracy, but you gain explainability.
Yeah, no, that's true. It's something which is basically, it's usually named as, oh, the reason why explainable AI is difficult, because you have this trade-off. And there are also people who think differently. I think there's this nice article from someone, Rudin, I think from 2018, and it's titled something like "Stop Explaining Black Box Systems and Use Interpretable Models Instead," where she basically argues, okay, these models usually that are more interpretable, like, I don't know, decision tree or something, for a lot of things, they're just fine. So you don't really, people should actually just not trying to get out the less bit of performance and just use other models if it's necessary to be able to explain them. And I think in practice, maybe that's quite often just good enough. But then, on the one hand, you always have this problem that people will still be using the other kind of models, right? So you can force them to do something else. So either you, I don't know, outlaw that, or you try to explain them. And also in a more like theoretical sense, for some purposes. So for example, these kind of visual systems, right, where you take in an image and you get some sort of output, they are generally not really, you can't really replace them by a decision tree or something. You need some kind of processing to happen before that is a little bit black boxy at least. So I think there it's more reasonable to say, okay, you can't just replace the models. There is some sort of trade-off, and maybe a quite large one. So then it remains interesting, like, okay, how can you make these models explainable, right? So how can you get some idea maybe of these features, maybe of some other kind of way in which you can talk about the things that they are doing. So it depends on the scenario, but I think in at least certain contexts, it's still a very interesting question, but not so much in a sense of, is there a trade-off, but more like, is it possible at all, So in a more theoretical sense, I guess, is what I'm interested in.
Yeah. Okay, thanks.
Maybe, Nardi, I have a next question.
Mm-hmm.
And I'm not sure how to phrase the question, but I'm trying to figure out how I can connect your position to some other ideas in the literature. So and there's two ideas that I'm thinking about. So the first is what I didn't get, what I didn't see when I read your thesis, but what my impression is during your presentation today is that you present the Mars levels, or even something like Clarion, as that it's relative reductionist. So I guess my first question is, do you think of these methods and as the position as that it is reductionist?
So do I think that this idea of, you can always look at these kind of three levels, for example, that is reductionist, or?
Yeah, because the way you explained it today, or at least how I understood your explanation today, there's a sense of direction. So you have a bigger concept at the computational level, or some goal or objective.
Yeah.
But it's reduced to the neural implementation, the neural substrate. And similarly here in the Clarion picture that's still on my screen, the idea is, right, these rules are instantiated in a neural network where I can see an input layer or an output layer. Is that your position as well, that it's reductionist? Well,
so in my thesis, I talk quite a lot about these different kinds of levels and how they relate. Yeah. And so first, so I guess it really depends.
Okay, that's a good answer.
Yeah, it depends.
It was a trick question, so I'm happy you say that. Your thesis are more nuanced, yes. But explain why you think it depends.
No, of course. So first of all, you have this. So if you're talking about, okay, what is a system doing? You can always kind of go back to this implementation, because in the end, that's what's really going on, right? So you can have that as a sort of Yeah, so that's the only thing you can really be sure about, I guess. So in some sense, that is kind of a reductionist position. But then, if you actually want to talk about what the system is doing, you're always going into some level of abstraction, right? Unless you really talk about this neuron is connected to this neuron and this, you're always going to have some sort of abstraction. And so I think when you talk about explaining, where the point of explaining is not really to know what's going on in the system exactly, but more to have an understanding of it, which is a little bit more, I guess, vague kind of a concept. And it's difficult to define what does it really mean to understand something. Is it just to know everything that's going on, or is it something else? So I think it's not from the point of.
Sounds good. But I'll add my second part to it, because I think this interesting bit is still to come. Because the other thing in your thesis, at times you discuss that it's a lot about what's going on internal, but sometimes there's also something external. So to me, that triggered the whole context of situated cognition, embodied cognition, the sense that we are placed in a world, and that's why I tie it to the reductionism, right? That's one place where the reductionism fails. So I guess have you, and this can be maybe a short answer. Have you thought about what the places of your idea, the concept that you propose in light of such situated embodied cognition positions? Like, is that consistent, or is it very different?
Yeah, well, I think it's there's an interesting connection, because in some sense, when you talk about this kind of situated cognition, for example, that means that if cognition is situated, you can't really talk about it in a very you can't talk about it only at this implementation level, for example. You have to look out sort of into the environment, into the context in which it is taking place. And I think a lot of the times when you go to some sort of higher level, you already do that a little bit, even though you're only talking about a system itself. You're already bringing in concepts from outside the system, which you could say, a neural network doesn't really know something about a spider, but if we call it a spider, then it sort of does. Well, that's a little bit strange to say, but yeah. So I think something like situated cognition is very much also about having these also looking at these, for example, not looking at a single level, but also going sort of higher in sort of the hierarchy. I think that's important. Yes,
I'm happy with your answer, because I also think it I guess that's a kwartje dat op zijn plek viel during the presentation, of lacking the English term.
Yes.
But I guess one argument that comes from your thesis is this idea that we're maybe over-fixated on the neural implementation, as you said before, with these deep convolutionary networks, for example. Whereas I guess the success story of the cognitive science side of the cognitive architectures and these Mars levels is that different explanations can coexist. And sometimes we might not, to actually answer the question we're really interested in, we should move away from the implementation level and look at the computational level or the algorithmic level. So that's a nice, I guess that's one way maybe to even if you were to rework your work, to put that more central, that you can say, well, that's a success story in the cognitive architecture world. And why don't we do that more in the neural net, the more computer science neural network architecture? Because I guess you have been making that argument, but only today it settles down for me. So, okay, I'll leave it at that for my questions. Thanks.
Okay, no problem. Thank you. Oh, there's a question in the room. In the room. Ooh. Okay.
So I have a question that is a little bit related to this. When you present the levels of MAR, you present them kind of as a ordered sequence rather than a set of levels. So you have these like things, and it's like a continuous scale almost, where you can have things in between, like computational and algorithmic, or in between algorithmic and implementation. But what I was wondering about, if you see this order from computational to implementation and algorithmic in between as necessary, or do you think that it's possible to have certain aspects of a system that hang in between computational and implementation without getting closer to algorithmic? So rather that you would...
so could you like do it like, instead of only going like this, could you go like this, right? So you go down and then go up or something, but you go two ways.
Could you,
now what I for the camera?
mean is, like, could you, for example, turn algorithmic and implementation around? Is like, is the order from computational to algorithmic to implementation, is that the order you see kind of as the way it's supposed to be, and things can only be in between computational and algorithmic, or in between algorithmic and implementation, but not be in between computational and implementation and not be closer to algorithmic? So kind of if you have your scale, could you turn around the different points of the scale, or are they always necessarily organized the way you organize?
Well, I mean, I guess it depends on how you, that's always the first part, it depends, but but really, depending on the way how you define them, I guess, you can do it in some way, at least in the sense of, so what we see in these kind of, for example, when you're training a neural network, we see that you skip a part of the, sort of, if you do have it as a vertical spectrum, you kind of skip a part. So that is possible, at least. So you don't need to always sort of, they're not that sort of essential in the sense that you need to have the three of them and they always sort of work in the same way. I think you can look at them as a bit more just a sort of a nice way to think about the system, and not really sort of a necessary way to think about the system. Does that make sense? Yeah. And then the order, I think how they're defined, it's quite strict in the sense that one is sort of higher level than the other. So no, you couldn't really do that, I think. But yeah, I mean, in some sense, it just depends on how you talk about it. But I guess maybe what you're more getting at is, do I think that it's sometimes reasonable to maybe talk about different levels which are not just like on a string, but have sort of different paths going from up to down, or...
Yes, I guess that's what I mean. Like,
just in general, like, is that maybe...
Yeah, and I was also thinking about, well, obviously computational and algorithmic are very close. Like, often when you want to know why a system is doing something, it's gonna be an explanation, maybe partly in terms of the algorithmic system. Kind of like, what steps does it take, and it does not always have to be the case, but sometimes it is. So I can make it's reasonable for me that you order these kind of next to each other. But then I was thinking, you can also think of things that kind of hang between computational explanations that hang between those two, but have nothing to do with the algorithmic level.
And do you have an example of something?
Well, I thought maybe these kind of evolutionary explanations, they often kind of appeal to biological explanations as well as more theological. So, like, with what is the purpose of the system?
Well, yeah, so I get what you mean there. I get what you mean. Yeah, and I think maybe, I guess, right? So in Mars hierarchy, if you start to look at the outside world, you're pretty much in the top, I think. But then if you also really sort of go into these very specific things, like maybe some gene or whatever, it's also like very much implementational. Yeah. But I think also not, I don't know, it's a bit difficult to, right, you can look at it.
Maybe I guess that's Fleur, isn't it, who's asking the question?
Yes, it is.
So both of you have done cognitive modeling. So you reread the House and Lewis paper, as I think they discuss about that bridge. I think evolutionary algorithms, they're necessarily at the computational level, but they are they could be implemented as a neural net, but there's no claim that that's the instantiation in the brain, right? That's how it's developed. So a technique. So in that sense, it bridges implementation, but it's not really implementation. But there are the model that they propose is that some form of algorithm approximates those two, right? So we've discussed that example of the psychological refractory task and of a word reading task, where you do see elements of both, where you say, well, here's a little bit of a neural network being trained, but here's also a high level objective that we try to achieve. But those are relatively rare. I think the connection, there's more like a connection algorithm to one of the others than really between implementation and computational. Anyway, but both of you have those papers, so given that you're interested in, we'll talk about some other time.
Also, just in my thesis there's a lot more. So I also talk about different kind of I don't know, ways to think about the levels or whatever, and I talk a lot about the distinction between competence and performance, which is again like really sort of different, but also a little bit similar. So I don't know, there's some more stuff in there as well, but yeah, it's a lot to talk about here.
Yeah, and I think we are about out of time for the Q&A.
Yeah, I think so too.
So thanks for the answers. And now I will take a quick break together with Chris Jansen to talk about evaluation, and we'll be right back in 5 or so minutes. Hopelijk vond iedereen deze meeting geschikt, ook al was het natuurlijk digitaal en in tijden van corona moet je het anders doen, maar mijn indruk was dat we een leuke presentatie hadden en ook een goede discussie. En Chris en ik hebben net onze indruk besproken, en zowel van de scriptie als van de presentatie. En trouwens, ik doe dit even in het Nederlands als dat mag.
No, is illegal.
En we willen nou een eindcijfer van 8 geven voor het hele project. En we waren onder de indruk van de brede aanpak van zowel de scriptie als de presentatie. Nou, die is duidelijk goed thuis in een aantal velden, in de filosofische aspecten, de meer praktische implementatiekanten. De scriptie is ambitieus en ook origineel. We zien daar een zelfstandige creatieve denker aan de slag. En dat stelden we erg op prijs. Als je aan zo'n ambitieus project begint, is het natuurlijk van tevoren de vraag van, in hoeverre zul je een antwoord krijgen op je kernvraag. En daar hadden we misschien enige bedenkingen bij, maar verder vonden we het een hele brede, ambitieuze, interessante scriptie. En we gaan dit nog meer duiden in onze uitgebreide beoordeling. Dus alvast gefeliciteerd met een goed product.
Dankjewel.
En ik wil ook enkele dingen zeggen over onze persoonlijke samenwerking. We mogen even applaudisseren, dat maakt natuurlijk altijd. Dus ik heb met Narbi overleg gehad en samengewerkt de afgelopen 3/4 jaar. En het was voor mij een hele prettige ervaring. Ja. We hadden altijd een leuke connectie. En nogmaals, ik zie in jouw werk een creatieve, zelfstandige, zorgvuldige denker. En, dus we hopen dat je dat voortzet. En van mijn kant was de samenwerking heel plezierig. En ik wil trouwens nog een correctie aanbrengen. Dat spelletje in je presentatie was denk ik niet Frogger.
Dat was een soort gekke variatie van
Frogger. Boulder Dash. Dus aan je rekenkennis moet je nog een beetje staan.
Nou, dan ga ik inderdaad even opzoeken. Ik dacht dat ik iets van Frogger had zien staan, maar het is inderdaad wel een gekke versie van Frogger hoor, die ik ook niet herken.
En nogmaals, gefeliciteerd met een topscriptie. En we hadden ook al even contact gehad over of we dit kunnen herschrijven en verpakken en misschien ergens naar een journal sturen. En dat is denk ik ook
een klein stukje dan tenminste ervan.
Proberen waar. Dus daar wil ik bij laten.
Oké, dankjewel.
Alsjeblieft.
Nou.
Gefeliciteerd Nardi ook van mij. Rand heeft alles al gezegd, dus ik wens je veel succes in je carrière. Blijf in contact, dat is altijd leuk om van masterstudenten wat te horen. Het is nu een beetje gek hè, net op afstand, maar ik vind het altijd interessant om te horen wat studenten daarna doen en hoe ze zich ontwikkelen. Dat geeft altijd weer inspiratie voor de huidige studenten. En ik vind zeker ook bij jouw scriptie, dat heb ik niet met Brand gedeeld geloof ik. Maar we hebben een tijdje, alweer een jaar geleden voor corona, hebben we onderwijsvisitatie gehad. En toen zijn we, dus dan beoordelen ze de opleiding. En toen zijn we heel erg doorgezaagd over of je ook met een filosofie-scriptie mocht afstuderen. En wat heel leuk was, is dat daar zat het hele docententeam, dat het hele docententeam zei, ja dat mag. En dat is heel goed. En daar zijn we heel trots op. Dus ik vind het ook heel leuk om dan nu, dat was nog volgens mij voordat wij dat hadden besproken, maar dat ik dan nu ook zo'n mooie filosofische artikel mag zien als eindscriptie. Dus
dat gebeurt niet zo heel vaak.
Nou, de visitatiecommissie zat te zeggen, moet je niet altijd wat programmeren voor een AI-scriptie? En daar waren wij het allemaal unaniem mee oneens, dat het niet per se hoeft. Dat werkt, en de visitatiecommissie was uiteindelijk ook overtuigd. Dus dat staat heel expliciet ook in het rapport, dat dit een feature van Utrecht is. Dus jij bent een feature van Utrecht. Daar ga ik het bij laten, want het is veel leuker. Jullie hebben daar nog wat persoonlijk om erbij te doen. Ja, veel succes. Hopelijk komt er nog ooit iets van een mooie uitreiking. En dan, wie weet, zien we elkaar daar dan weer. Dat is allemaal een beetje afwachten op het moment. Maar goed. En ook gefeliciteerd aan jouw familie die op de call zitten. Maar die spreek jij en vier jij het vast ook nog wel mee. Dus,
spreek ik denk ik later nog.
Precies. Hey, ik ga eruit. Veel plezier. Doei. Dankjewel.